I'll move on to the next speaker, who is Ed Galea from the Fire Safety Center and the Center for Numerical Modeling and Process Analysis at the University of Greenwich, and is going to talk about FSEG COVID19 mitigation analysis using CFD and agent-based model. Ed, if you're good to go, all yours.
Thanks very much, and thanks for inviting me along to this presentation. I hope you can see my screen without all these other things in the way. But just to emphasize, this talk is a result of work by the Fire Safety Engineering Group. I've listed all my colleagues on the first slide that have contributed to this work. And I'm going to be talking a little bit about agent-based models, but also about our CFD models, because I really don't think you can use agent-based models on a fine scale, say a building scale, without taking into account impact of the different vectors for infection. Just a very brief overview of the Fire Safety Engineering Group. We're a team of about 20 full-time researchers. We've been working on for 30 years, developing agent-based models and computational fluid dynamics models. We have models for building-sized environments, transport environments, and urban scale environments. And we also do a lot of work in understanding the behavior of people, how people react and behave to quantify what we have in our models. If we're going to talk about infection probabilities and mitigation strategies, we really need to think about the three main ways in which COVID can spread. And the first two are listed here. The large droplet concept, where you have large respiratory droplets greater than about 100 micrometers. These are like cannonballs, and they follow trajectories that fall to the ground in seconds and within about 2 meters. And the susceptible population is infected either through inhalation of these large droplets or with the large droplets falling in, for example, the impact of the eyes. And from this concept, we had the recommendations of 2 meter physical distancing, avoiding direct face-to-face contacts, face shields, partial shields, and one-way systems, none of which was validated in any way as to the efficacy of these approaches. The second vector is the formite infection. And this is where the large droplets fall on surfaces. You touch the surfaces of your hands, and then you touch your face and spread the infection to your face. And hence we had this, Macbeth period where everyone was washing their hands excessively. And today, the CDC has announced something like this form of infection is probably less than, you have a 1 in 10,000 chance of being infected through this route. Now, based on these, we've developed agent-based models, and this is an example of the Exodus agent-based model. The animation you see on the right are the agents trying to maintain a 2 meter physical distancing. We can build this into our agent-based models, change the behavior rules, so the agents attempt to keep physical distancing. And this is very, very useful for calculating things like the impact physical distancing has on capacity, for example, level of service, and throughput through a structure. In this particular case, for example, there's less crowding at the exit, and but the time it takes for people to transit through this is increased by about almost 20%. Now, the difficulty with this is that it ignores probably the most important vector for transmission of COVID, which is the airborne infection route. And this is due to small respiratory droplets, less than about 100 micrometers. Now, these aerosols can be dispersed through the air as a result of the ventilation system, the thermal effects coming off people's bodies, and the wake effects caused by the movement of people. So the actual movement of the agents will affect the way the aerosols are dispersed, and hence the probability of infection. Because of the aerosol route, we have the recommended mitigations of wearing face coverings and having high ventilation rates. So in my opinion, this is why agent-based models on a building scale are not very useful for determining infection probabilities or assessing the impact of mitigation strategies, because they effectively ignore this concept. You can calculate a proximity dose, but that just really takes into account the first mechanism of the large droplets. So right from day one, we started looking at, we were concerned about aerosols right from day one, and we started looking at how we could modify our CFD software to incorporate dispersal of aerosols. And so we modified the capability of the software so that we can represent both the dispersal of aerosols either as a passive scalar or as evaporating particles. We've introduced the capability to represent HVAC systems with filtration, and we also have a capability now to simulate the impact of the wake caused by movement of people as they move through. One of the unique things that we did right from the start was that we coupled our CFD software to the Wells-Riley model so that we could take the concentrations of aerosol and convert that into an infection probability. So it's not just talking about concentration, we talk about infection probability. And the work we've been doing with this is attempt to verify our model using real world data, and also applying the model to try and simulate other situations so we can come up with mitigation strategies. We've got several publications. There's one publication on an in-flight infection risk. There's another paper that I'll be talking about in this presentation, looking about infection on trains. And we have another paper with another RAMP group that is currently in review, looking at issues to do with how you model this in CFD. One of the first things we looked at is the impact of aerosol dispersion on aircraft. The aviation industry has published a lot of stuff saying about how safe aircraft are from COVID. And this is because of the claimed high ventilation rates and the use of HEPA filters. And this is some work that was published by Transcom and Boeing fairly recently, which measured in flight the distribution of aerosols in this experiment. And what they found was that because of the high ventilation rates and the use of HEPA filters, the concentration in the measured area in the cabin section could be reduced by 99.99% from the source. Now that's really fantastic, but they concluded from that, incorrectly in my opinion, they concluded that this means that the risk of infection is minimal during these in-flight situations. And what we did was we took the concentrations from the experiments and we used our modified Wells-Riley model to calculate the risk of infection given the reduced concentrations the ventilation system produced. And what we found was that for a 2-hour flight, the infection risk varies. The maximum individual infection probability varies from about 4.5% in a mild scenario up to 60.2% in a severe scenario. And the average infection probability, if we took it over the entire section, varied from about 0.1% to 2.5%. Now, if we compare that with actual statistical data that's been published of infections on aircraft, what we find is that the measured infection probability, the maximum is about 10.1% with an average of 0.7%. And that falls very closely in line with what our simplified model is actually predicting. For a 12-hour flight, what we found was that infection probability varies, the maximum infection probability varies from 24.1% up to 99.6% for a 12-hour flight. And the average infection probability varies from about 0.8 to about 10.8%. A huge mitigation, a very successful mitigation, is if everyone wears masks. And if you wear masks, you can reduce the average infection probability by about 73%. But what we found also is that if you remove your mask on a 12-hour flight for a 1-hour meal break, you then increase the infection probability by about 59%. So basically, the conclusion and all the misinformation that the aviation industry is putting forward, that how safe it is on aircraft, you really need to take that with a pinch of salt. The next thing we did was then we looked at how to verify our CFD model, and we're using this real data from a Chinese study of infection on their high-speed trains. They studied over a period of time from December 2019 to March 2020, something like 2,300 actually infected index patients that had boarded the trains, and they looked at 72,000 contacts on the train, and they did quite a detailed study of this. And what they found was that the infection probability in these carriages was about 10.3%. The thing to note about these carriages, they're different to the UK carriages. They have extremely high ventilation rates, 44 air changes an hour and 24 air changes an hour, whereas on the UK trains, it's more like 8 air changes an hour. So we've got that data to compare against. So we modeled it using our CFD software, and we're using our scalar model for gas release. I haven't got time to go through the details here, but essentially we model a source of infection in each of the 5 seats separately, and then we combine the data to give you some sort of average overview of what's going on. And we look at, we take into account the ventilation system and the filtration system on the train in the CFD software. We also did a mesh sensitivity study to identify an appropriate mesh to use, and we ended up using the medium mesh, which gave us pretty good agreement with the very fine mesh. So most of these calculations are based on the medium mesh, which is pretty good, and it's about 2.2 million cells to model that one carriage. Now, this is our modified Wells-Riley equation that we use in conjunction with the CFD model, and this takes into account the percentage of people wearing masks, because not everyone on the train wears masks. And in these calculations I'm going to show you, the assumption is that 40% of the passengers are wearing face coverings. Okay, and if we now compare our CFD predictions against the measured data, what we find is that what was measured was that there was 10.3% maximum infection probability for the person seated next to the infected person. And in our CFD simulations, we end up with 14.7%, which is pretty close. And if you also look at the average, the seat that had the greatest infection probability and the least infection probability, we're getting similar results from our CFD calculations. And what I'm showing you here is 2 graphs showing the infection probability as a function of exposure time. These journeys are up to 8 hours. The squares represent the measured data, and the solid line represents our models. And I think you'll agree we've got pretty good agreement against the measured data. So we've got some confidence that this model is doing something that's reasonable. If we now delve into what the model is saying in more detail, this becomes very interesting. One of the things we see is that this diagram here is showing you the quanta, if you like, the concentration of aerosol based on a passenger, infected passengers in seat 6C. And what the first thing to note here is that there's a very asymmetrical distribution of concentration of aerosol. And that means that there is an asymmetric infection probability distribution. And the diagram below shows you the infection probability for each seat in percent for the passenger, the infected passenger seated in seat 6C. And it's really important to note that there is an asymmetric distribution. So it's not a circle around the source with equal probability of infection. It is very significant actually behind the seats behind the infected passenger compared to the seats in front. And the seat obviously next to the passenger has got a very high probability. So that gave us some detail into what's going on inside the train. And also it shows that the coarse assumptions that are usually used when you just simply use the Wells-Riley equation are really not applicable in these cases. The Wells-Riley approach assumes you have a uniform distribution of quanta across the entire volume, and that's simply not happening. And so then we looked at different mitigation, non-pharmaceutical mitigations, and what effect that would have on infection probability. And so we looked at various things. So if we increase the ventilation filtration to 100%, so a super HEPA filter, the maximum infection probability only decreases only a small amount. the maximum, but the average decreases from about 1.2% to about 0.6%. And so the number of infected people on board, predicted secondary infections, go down from 1 to about 0.58. If you change the ventilation rate, if you decrease it down to the sorts of levels that we have on UK trains, you see that the secondary infections go up from about 1.1 to 2.2, so low infection, higher number of secondary infections with the lower rate. And wearing masks has a huge impact. So if we have 90% of the passengers on board wearing masks, remember in the base case, only 40% of the passengers were wearing masks. If you increase that to 90% wearing masks, you reduce the number of secondary infections from 1 down to 0.6. And if you give all the passengers N95 masks, so 90% of the passengers are now wearing N95 masks, you reduce the secondary infections down to 0.05, a huge impact. And then we also looked at seat blocking strategies. What if you start leaving out seats, passengers on seats? And the most effective seat blocking strategy basically meant you had passengers seated in the A, C, and F seats in odd rows. And this would reduce the number of secondary infections down to about 0.16. Now, clearly, if you're doing this seat blocking, you've got 3.15, you've got much fewer passengers on board. And so to have the same, to transport the same number of passengers, you'd have to run 3.15 times as many trains. We also looked at the impact of inoculation. And here we have, we're using the data for the 617 variant. We have 51% of the UK population has got 1 dose, and 30% of the population has got 2 doses. And the effectiveness against the 617 strain is indicated here. This is from the data from the PHE. And if we build that into our model, all that's doing is reducing the infection probability by about 40% in this situation. And so this reduces the number of secondary infections from about 1 in the case where there's no vaccination to about 0.6. So there's still a significant risk of infection, even though you've got a vaccinated population. The very last thing I want to quickly get on to is that we also model the particles instead of just looking at the treating the spread of the aerosols as a scalar. We can also look at a particulate approach, as I'm showing you here, and this becomes particularly important when we're looking at the impact of people moving and walking in corridors. And I hope you can see this. There are 4 people walking here, and here we have the lead person emitting a cloud of aerosols which are infected with COVID. And as you can see, each one of those agents that are following are 2 meters behind the person in front. So the 2 meter separation really doesn't give you much protection from this aerosol cloud. And so you really have to question the use of agent-based models and just looking at a dose based on the 2 meter separation concept. I haven't got time to talk about this, but we're doing similar simulations in buildings to look at the impact of ventilation systems in buildings. I just want to quickly go on to my conclusions. As I see, I'm running out of time. So to conclude the presentation then, agent-based models can provide insight into the negative impact of physical distancing, but usage of agent-based models is limited to capacity, throughput, and level of service analysis. You can also do proximity dose, but the proximity dose should not be related to the infection probability. That's a mistake I think many people are making. To understand the potential impact of dispersal of contaminated respiratory aerosols on infection probability within complex spaces, it's essential to consider the impact of convection currents from body heat, the natural and forced ventilation, and its interaction with the spatial configuration, the wake effects caused by moving individuals, and all of this requires a CFD analysis. These factors can generate asymmetrical dispersal of contaminated aerosols, drive contaminated aerosols in unexpected directions, not this simple 2 meter diameter circle, and generate persistent hotspots, severely impacting the ability of agent-based models to predict infection probability and the effectiveness of mitigation strategies. Within complex spaces, the desirable simplifying assumption of a well-mixed environment, and hence the appropriateness of simplistic treatments such as Wells-Riley model for mitigation analysis, is questionable and potentially misleading. Simply imposing high air change rates may not be sufficient mitigation strategy. HEPA filters alone may not be a sufficient mitigation strategy. Masks can be very, very effective, but requires public buy-in, adherence, and education. And partial inoculation and population immunity can be factors that we build into our models and hence calculate infection probabilities. What we are currently doing in my research group is we're currently exploring the development of a new coupling between agent-based models and CFD to enable the agent-based models to move the agents in the CFD model so that the agent-based model is propelling the agents around the space. Thank you very much.
Thank you very much for a super interesting talk. I'm afraid in the interest of time, I might leave you to have a look at the chat, and because there's a couple of questions. There's been quite a few questions actually on your talk, but we don't have any time, and I'm conscious that I want to leave the last speaker enough time for.
Not a problem. I'm happy to take questions during the coffee break as well.
Yeah, and maybe perhaps that's another option. So let's move quickly to the next. And